Thank you for the applause. Welcome. And thank you for participating in this talk. And thank you for staying until the end. It was a very tough day, difficult and intense. And in our talk today with Gervasio and with Paula, we will talk about the results of the last crop service for service crops. Mr. Piñeiro is an agricultural engineer from Uruguay and a doctor in agricultural sciences from the University of Buenos Aires. He is currently an assistant professor at the School of Agronomy of UBA and a professor at the School of Agronomy in the University of the Republic. He is also a principal researcher at CONICET. Paula Berenstecher has a master's in environmental sciences and agricultural sciences in UBA, and she is a teacher at UBA, and her research is focused on understanding the decomposition of organic matter in agroecosystems. So the talk that we will hear now and that we will be sharing will include the results of the crop season 2023-2024. And to begin, in the service crop network is part of the chakras system of Aapresid, which was created to respond to the needs with technologies that are sustainable. And what distinguishes us is a systemic vision in the approach of problems. We work with two flags or two representations. And the space of the chakra system, which is part of the network, and we have more than 10 projects, we have three main pillars: farmers and consultants who carry out the trials and the tests and provide us with the information that we will be sharing. We have the companies that provide resources and technologies, where we are constantly testing new tools, and where we also put the theory to a test. And also experts, Gerba and Paula, who will be talking today, but there's a huge team behind them. Thank you for participating, and thank you for developing a teamwork. I will give the floor to them. Thank you very much, Lina. Good afternoon. It is a true pleasure to be presenting the results of our network this year. We've been working for 6 or 7 years nonstop. And today with Paula, with Viviana, who is behind the numbers that I have shown, we will be showing the data. And the data is actually generated by the real heroes of this movie, Rodrigo Penco, Ramon Roldán, Franco Bardejia, Franco Scalora, Celeste, Alfonso, Juan, and Victoria Campos, each one in their region. They are the ones who do the tests and are responsible for this work. To start, the questions change every year based on the demand. And we are constantly talking about what species, yes, and what species correspond to each region, to each zone. So we are trying different species in different areas, but with more emphasis. And seed companies, of course, give us a hand. And the production of air biomass, and we will be showing the production of roots, which is very complicated to measure, but we did an experiment at the university where we measured almost 30 species in the production of roots. We will be seeing that as well. And especially the time element here. So when, not only what, but when, thinking about that window of opportunity for service crops. We always repeat this. To do a good service crop, the key is to define the window and for water to be the exact amount necessary to not affect the actual profitable crop. You know this very well, that in dry years this is very difficult. So understanding the timeline is very important to define the window and to finish these service crops when necessary and not afterwards. In association to this, we will assess the consumption of water and the effect this has on the yield, which is the profitable crop that we are interested in. one cannot see this very clearly, but this year we have 6 sites, 7 with the experimental site at the university, which is here in Buenos Aires. And we also have Vila and Paraná together in blue because it's places where there was a lot of water. We will analyze that area. Valdicera and Godoy in red because they're both going towards soy. In Paraná, they're going towards maize. And the dry areas are marked in red, and in green, San Agustin and Quenuma, where there was a normal amount of water in the last season. So we will see what happens with the crops when there's more water, less water, and the different areas as well. This map shows the pie charts. The pie charts show the amount of biomass that was produced. At the experimental site at the university, it's the biggest pie chart because it's where we had the greatest production, a warm winter with lots of water, so we had a very high production of service crops. Quenuma in the south, a site where they had good rain at the end, but with a lot of production for that area. They planted quite late in the season. And Paraná is the other production site. Remember that they were together with Vila. And Paraná had a problem, which was a lot of water, but late in the season. So they have a small pie chart because they had a lot of rain, but late in the game. So you know better than me when it needs to rain. And then smaller pie charts in the other sites because they were dry. The colors will always be legumes in red, in reddish tones, and crucifers in green. And you will see those colors throughout the presentation. So San Agustin, surprisingly enough, legumes produced more than,
como sabemos, siempre
because we know that they produce more. But if you can see in the upper part, and it was different. So we analyzed each site in particular. So we had biomass, air biomass that was produced, and the days from planting. And the last point is the harvest day. In Paraná, for different reasons, we only had 1 day of harvest, but in the rest of the sites, you will see something similar to what was shown in Vila, which were 4 dates of harvest that were different, and each color is a different variety. In blue, you have grass, and in red or reddish area, you have legumes, and in green, you have the other ones. And so if you take a look in Paraná, the typical situation was seen, not very good production because lots of water, 400 millimeters between what was there at the beginning and the end result. So that for all the process of that service crop. But like I said, there was a lot of rain, but late in the game, so they were not able to capitalize on that. You can see 12,000 kilos up there in Vila. You see how grass is at the bottom and legumes are located in the other position. And in general, what we see, and which is something that is repeated, is that grass, in general, we have barley as one of the most important productions. Albicias Casubi, in general, has the greatest yield, even though we are trying different ones in different cycles. With Pablo, we have the ones one of the vetches that behaves better. But it depends on the idiosyncrasies. So if we see what happened in Vila, here we see this trend in several, like radish or mustard seeds that we tried at an earlier stage, even before grass seeds, because in some they grew without problems, of course, depending on which grass seed we're talking about. But you can see that green goes down. So they have a peak after 20 days, and then they flourish, and then they drop because it's a service crop. But you have the problem of what happens in that gap after they reduce. You see how the blues go up, the grass seeds, and the legumes as well in pink, which are later, appear later. In the upper part, we have Viciaca subis, but we have a surprise in this site, which is that purple line that was very, very low at the beginning. We have a Melilotus, the alba that continues to be low, but Melilotus jachai munai, which is a blend of two Melilotus, you can see the exponential growth that it shows in the latest days. So they are very high up in the ranking. So it's an interesting blend of Melilotus, but with a late production. So if the window is not long, in the shorter windows, we could have more vetches, and some vetches, for example, are developed more quickly. But with Melilotus, it's really surprising to see how it moves to the highest positions in the ranking. There's an interesting aspect there where we have big windows there.
¿Qué pasó con el agua?
These were the humid areas. What happened to water in these sites? Water consumption due to the farro, cruciferous, and vicia what is the use in the case of fallow? In case of fallow, they evaporated 400 millimeters of water. You can see there on screen. Almost 300, 200 on the case of vetches. So fallow consumes a lot of water. It's not that they accumulate indefinitely. That's the water consumption in the case of fallow. How much? 400 millimeters. And in the case of service crop, they have the same type of water use. So there is no difference between fallow and cruciferous and vetches. In Villa, some of the dots are below fallow. That is to say that they consume less water than in the case of fallow, except for in the case of long oat Faraona. In general, when we have a service crop, water infiltrates more. So when we put fallow to take care of water, it doesn't take care of water. It spends more water or uses more water. They use the same amount of water. So when planted in the right time, if the dry part is done wrongly, it's a different story. Let's compare the yield. In Paraná, in this table, we can see the yield of corn with prior long fallow and prior service crops. If the dots are above, which one yielded better? The service crop. Otherwise is the corn after fallow. And what do we see there? It's corn of 1,700 kilograms because of the corn leaf hopper. But then we see that the service crops is above fallow. With lower yields, there's practically no difference. And that's the list of the corn that came from vetches that had the best yield, but with very little difference due to the corn leaf hopper. What happened in the other side, in Villa? So we see practically the same. Here we have soybean, and when we see red, those are pulses, and is below radish and mustard. The order is different. What does it mean? That the yield is better when it comes after pulses, but the yield is not so good after the previous corn. But there are others that are receiving better yields. What happened in the intermediate sites? We had San Agustin above in the north, and Kenuma that is in the south of the Buenos Aires province. Let's see, this is a year with rains that are sort of average, and we are in the north in Chaco. Have a look at this graph. The best yields are pulses, and that is quite surprising because they used to be below that line, almost 8,000 in the case of veggies. These sites have 200 millimeters, up to 200 millimeters, starting with 180 millimeters. They are taking water that is a surplus from the previous year. This brings about almost 8,000 kilograms. That's a lot of nitrogen. And grasses are below pulses, probably because pulses had a very good yield for that area. What happened in Kenuma? That's the south of Buenos Aires province, with normal rainfalls, 288 millimeters during service crops, and we have something similar, grasses above, pulses below that, but in a very good group with 8,000 kilograms of pulses. Melilotus stays the same, and it's pretty reasonable because it's more for the summer season. We see better yield in the north, so Melilotus stays there, but veggies work very well. Black barley is very precocious and very productive in the area, and we see that in different trials, and we do not see the precocious behavior of radish that we saw in the past. That happens in the center of the country, not in the south. Every year is different, so we will see. But we have grasses there. What happened with water? In San Agustin, in the north, once again, we have the same graph. Fallow used almost 200 millimeters of water, and the others used more water than fallow, but there was not that much difference in Kenuma. It depends on the rainfall. In this case, there was almost no difference. But after fallowing, after the fallow, what happened with water? San Agustin went from more water consumption to less water consumption when they grow the summer crops after fallow. And in Kenuma, that there was no difference, there's still no difference in water consumption. When we have the right fallow, water consumption for fallow is big, but it's also similar to water consumption for service crops. What happened with yields? In Kenuma, there's something quite surprising. Everybody started, corn was above every crop, even grasses. Veggies, hairy veggies, ascasubi is differentiated from the others because they always tend to have very good yield. But cruciferous and grasses had better production, very good yields compared to fallow. Fallow is between 3,500 kilograms, and we are having 6,000 kilograms there. That happens in Kenuma. What happened in San Agustin? Well, we did not see the same pattern. We see veggies with a better yield, always up, certain pulses, and then grasses below and some pulses. But if you see the order, those that are having the not such a good yield are the red clover or radish. So a pulse that produces a lot before corn increases the yield. What happened in the dry areas? We are talking about Baldicera and Godoy. Here, there was 228 millimeters of rainfall during the service crop, and something similar in Baldicera with the grasses, much higher than in the cases of pulses. And in Godoy, we see that the green spots show the pattern of radish as the most precocious crops, but grasses are more precocious. So when there's little water, radish do not bloom so fast. And we have oats, barley also. And then pulses start blossoming later on. Meliloso goes up and starts going above pulses, the blend Yatai Munai, so it's higher in the ranking compared to pulses. It's an interesting species. What happened with water? The dry cycles, we see that fallow used up less water, and service crops uses more water. In Godoy, we had a problem with the scale, so we do not have data for Godoy, but I'm sure it's pretty similar to Baldicera. The service crops uses up a lot of water. But you see that the difference is narrower. There is a 50, 70 millimeters difference, and here we have smaller differences, 20 millimeters, and certain service crops are just at the same level of fallow, depending on how they performed. Baldicera had the pulses with a better yield, grasses with a lower yield, but when we see soybean, soybean does well when they come after pulses. Pulses are favoring soybeans, and grasses are providing a lower yield. In Godoy, we see the same with certain oat, with the sativa oat, with a positive trend, and all the grasses that the pulses that are below are red clover and some pulses that do not blossom, that have a positive impact in the soybean yield.
Muy buena.
A very good soybean, as you can see in the numbers, and the impact of having fallow before is almost 1,000 kilograms of soybean. And in this stage, after all these experiments, in one of these two sites, in Godoy and Baldicera, we measured roots. Elena measured them with her team, and we saw this dynamic. Paula will show the same graphs for the Buenos Aires experiments with many more species. And we saw the dynamic that allow us to see their performance. And this is the root performance. What did we expect to see? The root performance to be high at the beginning and then to get saturated. But we do not see that except in the case of mustard seeds and a bit for radishes. But in the case of grasses, they continue producing biomass in late stages. Paula will show us in further detail. We will see the curve later on. Roots produce biomass at the beginning, and then they stabilize, and we wanted to check that information. We have a lot of underground biomass afterwards. And this is similar to what happens in Baldicera. A lot of aerial production, the last third of the service crop. But there is a shooting of the underground biomass. The red clover lags behind, but the rest still goes up. Service crops at the end of the day continue producing roots for a long time. Not so much during the peak of it's blossoming. But Paula will share these small plots experiment. She will share the dynamic for root performance. We decided to show these data separately because this side that we added to this network is different. It's an experimental plot that is in the School of Agronomy of the University of Buenos Aires. One of the main differences is that we grew this species in microplots of 2.4 square meters. We grew 22 different species of the same that we have grown in the other sites, and we added some additional ones. Plus, we added 3 different mixtures, 2 functional groups. So we have a cruciferous and grasses mixture, crucifers with pulses and grasses with pulses. Another important difference is that we grew at higher densities. We did a first attempt to grow with the same density in other sites. But the problem was that we had too much weed. The experimental field is surrounded by a public space, so in this first attempt, these service crops did not perform well. So we planted 10 more times seeds, and that brought about very good results. Then we diminish the number of seeds, and we got a good performance. If there is a lot of weed presence, if we grow more seeds, it could be a good option as long as you have a good amount of seeds, and we could do so. And then we did different measurements in July, August, and September, and November when we finished this cycle. We measured aerial biomass and root biomass in time, which is the most advanced study we have, but we also measured for carbon and nitrogen in that biomass, soil water, nitrogen that is potentially turned into minerals, energy absorbed in time, and phenology. It meant a lot of work with the participation of a lot of different people. There are 4 students that are there, Martín, Facundo, Agustín, and Ulises, that are developing their thesis, and they have a lot of different students and technicians, and so we were able to measure a lot of things, so it was a teamwork.
Entonces, lo que le voy a mostrar ahora.
So what I will show you now are the biomass data. Here is the air and root biomass, and we show for the different species and the mixes at the end, in November at the end of the experiment. So in green, you'll see the crucifers, in light blue, the grass seeds, in purple, the pulses, in pink, the velches, and the mix is at the end in orange, the vetches. And what we saw was the grass seeds were the most productive ones, both aerial and subterranean. They were followed by crucifers, then pulses, and then vetches. And the mixes had intermediate biomass, which was what we expected. I will show this more in detail regarding what happens in each functional group, but one important thing is that overall we had very high values of biomass. We had rye, which was in light blue and reached 20,000 kilos, and this is due to several aspects. Higher density of what we planted, but in the case of grass seeds and crucifers, we use the same density and in other sites. Crucifers between 30 and 50 per square meter, and grass seeds between 100 and 150. And in the case of pulses and vetches, we found that at the end there were more plants per square meter, approximately 90 for melilotus and 200 for trebles, and here for the mixes. So what we saw was a mix of pulses. The density of plants could be one of the causes of the high biomass that we found. but not in the case of grass seeds and crucifers. So in these cases, we think that the most important factor here was the climate. We had a very rainy winter, a very hot winter. We had 400 millimeters throughout the crop season. And in May and in August, we had extremely hot months with minimum temperature of 10 and maximum temperatures of 20 with days of 30 degrees. Very strange winter. So this may be the reason why we had such high biomass. And here you can see some pictures of the last harvest. In this case, we have the crucifers, but Agustina, who is doing her thesis with this data of the biomass, took a picture of all the species and the date of the sampling. And what we saw was that radish, the boquito radish, had the best performance, followed by daikon radish, and finally mustard. As you can see, it's quite yellow. In November, it was past its moment. You can see the grass seeds here, and we found that Oleum magnum had the biggest root. You can see it, the third bar from the right. This was remarkable because in other experiments, Lolium camaro was the grass seed that produced the most. But here we found the opposite. Lolium magno produced more roots than Lolium camaro. Triticale mole produced a lot of root as well. And Triticale and Lolium were not the ones producing more air biomass. The ones that did this was barley, rye. And one thing to point out is that if we only see the aerial biomass, we're missing out on what is happening underground. Grass seeds, you can see here on the left, have very fine, dense roots, which are very productive to forming organic matter, especially particulated organic matter, thicker, that are the remains of vegetable matter in decomposition. So if we want organic matter, the roots of grass roots will produce a lot of carbon in the soil. Here you see what happens with pulses and vetches in the aerial biomass. Vicia's Kasubi was the one that performed the best with 500 kilos almost. Melilotus Yachai and Melilotus alba show almost 8,000 kilos. And one of the very interesting things was that if we saw the root biomass of the other pulses, we saw a higher abundance than the roots for vetches. Vetches, regardless of their variety, none produce a lot of root. You can barely see that. So in the photograph on the left, you can see what the veg roots are like. They're very fine with not many hairs, and the Melilotus are thicker. Plants not only contribute carbon to the soil through the roots, plants also contribute carbon and soil nitrogen through rhizodeposition. Rhizodeposition involves a lot of organic elements that are liberated through the plants in the roots and are next to the root and are deposited in the soil next to the root. It has radical exudation, which includes sugars, amino acid, fatty acids, mucilags that are more complex elements and are very important for soil aggregation, and also fragments of roots that die and decompose. A few years ago, we did an experiment in plants in pots to see how much carbon these plants were contributing and how much nitrogen as well. And we found an interesting result. In these pie charts, we can see the contribution of carbon, and this on the left of the pie chart, all of that carbon, 61% was in aerial biomass, which is in gray, and 24% was in the roots in black, and there's 15% of carbon derived from plants that was in the soil, was in the soil when we finished the crop. And that 15%, we saw that only 2.8% was in particular organic matter, and most of it was in MAOM, which is organic matter associated with the minerals in the soil. MAOM has smaller particles, but it's very stable because these molecules are absorbed in the minerals of the soil and protect them from decomposition. So we saw that there's 15% of carbon that were not being considered if we only took a look at the roots and at aerial biomass. With respect to vetches, the plants were much smaller, so they contributed less carbon, and that's why the pie chart is smaller as well. 67% was in aerial biomass, and only 2.7 was in the roots, and that matches the results of this experiment with a photo of what the vetches are producing. But we saw that 30% of that carbon was in the soil as rhizodeposition, and most of it was mineral-associated organic matter in MAOM. And although vetches contribute less through roots, we see that in relative terms they contributed more because of rhizodeposition. If we compare this in absolute terms, carbon contributions, which is that green plus the purple, we see that it's not really different or significantly different. So the rhizodeposition perspective is the same in both cases. In terms of nitrogen, we also found something that was very interesting, which is that although vetches were smaller plants, the nitrogen contributions were quite similar to those of oats. In oats, 68% was in the aerial biomass, 12% was in the roots, and 20% were nitrogen contributions by rhizodeposition in the soil, and mostly in MAOM. With vetches, 60% was also in the aerial biomass, very little in the roots, 2%, but the contributions for rhizodeposition was 40%. So in this case, we found that in absolute terms, those contributions of rhizodeposition of nitrogen in vetches was more than in oats. So although in the roots there was a very small contribution for particulated organic matter, we are contributing a lot of carbon and nitrogen on mineral-associated organic matter. There's a poster on this matter right outside the room if you want to take a look at the details. And now the final thing that I wanted to show you were these biomass graphs over time. Here I show you the aerial biomass for crucifers and the different days. Previous graphs showed the different points, and now we see other harvests as well in comparison. So what we see is that mustard, which is the lighter green, for example, is an early species. It has a peak of biomass after 140 days, and then it drops. Boquito radish continued to grow throughout the experiment. With respect to root biomass, which is here on the right, you can see that the axes are different, and we see a very different dynamic. We're seeing that both mustard and daikon radish, which is that a lighter shade of green, have all the biomass, have already produced all the biomass, and they either maintain or drop slightly. On the other hand, Boquito radish continues to produce roots until the end of the experiment. Here you can see the vetches, the aerial biomass, root biomass on the right. And what we see is that most of the vetch variety have a dynamic that saturates between 140 days, where they've produced almost all of the aerial biomass. Those that go faster are Vicia sativa Hilario, and for Vicia ascasubi, or the ascasubi vetch, they produce the greatest amount of aerial biomass. In roots, we see saturation dynamic after 100 days. Almost all varieties had produced almost all roots, and then they either grew a bit or were maintained. There are two species that are a bit more productive, which are the white flower and the Biscayart, but the differences are not significant. So in general terms, the roots of vetches are quite early. And what's good about this is that if we do a short crop, we also have the roots and their consequent contribution, even if it's just for a few days. Here, what you're seeing is clovers and melilotus. What we see in the red clover, we see an early moment with a peak of biomass after 140 days, and then the biomass drops, whereas melilotus behave differently. After 140 days, and in the last period of the experiment, they grew significantly. And if we go to the roots, what we see is a very different dynamic from what we had seen in vetches and crucifers, because the production of roots at the end of the experiment was very important, especially for melilotus, and also red clover, where we saw a greater drop in that last period, but where the roots continue to grow. So it's interesting to compare these curves between aerial curves and the root biomass, because they are very different, which is indicative of the fact that we cannot infer what is happening underground based on what is happening above ground. Here you see grass seeds. Here we have some species that are more early, and they reach their peak of biomass as seen on the screen in purple, and we have black oats, black barley, which are all earlier crops. Rye was the one that produced the most, and which is in brighter blue at the end of the experiment, but after 140 days, they had produced less than the others. And as for the roots, we see a very different dynamic than what we had seen in vetches and crucifers. The roots continue to grow, especially at the end of the experiment. And Oleomagnum, which had produced more roots at the end of the experiments, after 140 days, ended up being one that produced the less. After 140 days, Critucale Mole had produced the most, and Don Marcelo Rye had produced almost 2,000 kilos of roots. Finally, here are the mixes. What we saw was that the mixes themselves were not so different. We had a mix of two functional groups, daikon and oats, black oats, and hairy vetch Ascasubi hairy vetch. And we can see how the roots were quite similar one with the other in these curves. So the differences that exist between functional groups when they grow alone are compensated when they grow together. We can see here that the mix of grass seeds and pulses were different at the beginning, but at the end of the experiment, the three mixes ended up having the same aerial biomass. With respect to the roots, we see a peak in the mix of crucifers and pulses, and we had seen that peak in radishes when growing alone. But after 140 days and at the end of the experiment, the three mixes were very similar. One interesting thing was that the root value were intermediate. And so the mixes with vetches produced more roots than the vetches alone. So the mixes could be a good option to include a pulse, which fixates nitrogen, contributes carbon in terms of soil organic matter. And with a mix, we can include a grass seed that will contribute a lot of roots and produce organic matter, particulated organic matter. And this is how we reach a good balance.
Y bueno, con respecto.
And regarding this experiment, this is what we've got. Thank you, Pau. Now to finish, these are the main written conclusions. If you want to take a picture of this slide, in any case, the report will be uploaded. But in order to revise biomass aerial biomass production, grasses are the most productive ones, but not always. In one side in San Agustin was the other way the other way around. But if we want biomass volume, grasses are the chosen crop. Also, if we want roots, Centeno Don Marcelo and hairy veggies are the most productive ones. But we see differences in the production rank. But it's best to check the most productive areas. We have to see this get consolidated throughout the years. Melilotus, Yatai blend work very well when we have higher temperatures in the north, and they produce very good biomass for late corn. That's very interesting. Not so much in the case of the south, in the colder area. Boquito is the best of radish. It's much better than daikon in most cases, and it's got a root that goes down deep, and so it's more interesting. In terms of roots, Paula has already shared with us, but grasses produce a lot. Pulses also, veggies do not contribute with roots, but they contribute with root deposition. But in the case of clover and melilotus, are going to produce more carbon for this area. The temporal dynamic vary depending on the site, so we cannot generalize. It depends on the site, but in general, grasses were the most precocious in the drier areas, and the crucifers in the most humid areas. If in crucifers are faster, and grasses in drier areas. Pulses are late bloomer, and they will contribute in different sites. In different areas, radish and mustard have a production peak earlier on, and then they drop, leaving empty patches. So we have to think of mixtures. We have to eliminate the crucifer. And we are choosing crops of a longer cycle because they produce faster with a good result. They are not pulses, but grasses. In the case of roots, crucifers and veggies produce roots in early stages. However, grasses and pulses produce roots throughout their cycle in later stages. Water consumption in general, as we said, and I repeat, long fallow take up a lot of water. The more it rains, the more water they use. And in average, it was 230 millimeters. But in other places, they took up much more. Sorry, less, between 100 and 400 millimeters of water. That is similar to service crops. And this can be seen in the summer crops in relatively to humid years. If fallow was good, the amount of water in the soil is the same with service crops than with fallow. In dry years, this is not going to happen. If the service crop is not well done, it will take up more water than the long fallow. But in some cases, they can use up more water than in the case of long fallow because it has more infiltration and water capture. So when the service crop is well done, we end up with more water than in the case of long fallow. And in the case of yield of the next crop, what we see is that for soybean is no surprise. When we come from veggies, soybean had a better yield. But when we come from pure grasses, things get complicated for corn and soybean. pure grasses, we aim at mixes. We have positive effects in structure and the contribution of different roots into the soil and in its yield. But clearly, pulses have to be in the service crops mix if we want to see immediate effects at least. Or long-term effects can be different. Be mindful of the negative effects of the service crops due to the immobilization of grasses. Very productive grasses immobilize nitrogen and they lower the yield of corn. But we see also in soybean when we see very productive grasses. And you have to be also be careful with fallow. All of this is we will see different, you will see different posters with all this data, and you will find all this information in these posters. And I think this is it. Thank you very much. Thank you for all the information you have shared. This is the QR code. If you scan it, you can have access to the latest publication of the journal. It's open source if you want to see more detailed information of all the sites and all the progress made until the publication date that was just a couple of months ago. As you very well said, Gerva, we will have the final report very soon with the all the grain data and the service crops data. I'd like to take this opportunity to give information regarding water, drying dates, and planning of service crops. You can get all this information in the podcast we recorded last year. You can have access to all that, all these podcasts called Cultivando Servicios on Spotify, and where we talked about water management during cover crops. So you can have access to that information through that media. And on the other hand, I think it's very important to share with you that those of you who came to the Congress last year, I don't know if you remember that, but there was a survey to co-create the network and we had a meeting with the participation of producers, researchers, etc., and with the results of the survey in that meeting. During this campaign, during the season 2024-2025, we will have 16 experimental sites from the south of Buenos Aires up to Tucumán, where we started focusing on regions, focusing on the Aapresid nodes, sorting objectives or separating species, objectives, sites, regions for the type of crop per region to contribute with more pulses, species, what is the timing, type of seeding, drone seeding, aerial seeding. It's going to be a challenge, but we hope that next year we will be able to share all this information. And I think, I don't know if I'm forgetting about something. Please help me. Well, thank you. We're running out of time. We have to leave the hall, but thank you very much for the co-creation of the network, which is the most important thing of this network, to be able to collect the data from all of you. Thank you so much.